How do you build a champion? In this era of Formula One, it takes a balance of skill and science, adrenaline and engineering, a passion for disruption from the design lab to the pit lane, and the drive to not only be faster, but more innovative than the competition. Today we find ourselves an hour's drive north of London at the home of one motorsport team whose mission is to win and to do it differently. Join me as we kick off this journey with a peek behind the curtain at one of F1's hottest and most competitive teams, to explore how engineering simulation is helping to unlock a competitive edge and push the boundaries of what's possible both on and off track. I'm Miss Emma Walsh, and this is Driven by Simulation.
Formula One is very much pushing the boundaries, and whether it's on track, whether it's off track in the software and how we utilize the software. Well, at the moment it's all about development during the course of the season. Of course, with a cost cap, you've got to be efficient, you've got to be effective of where you choose to do your development. So the team are in that process at the moment, in that cycle, and then very shortly they'll be starting to think about next year's car as well.
Christian, what's the balance between the driver, the strategy, the design, all of this in order to win the race?
Well, they each play a key role. So, of course, you've got to have a design philosophy that works, that delivers on track. You've then got to produce and develop that design. And then you've got to operate it. It's got to be reliable. You've got to get your strategy right. And then, of course, the driver, who is our biggest variable, have got to do their part and deliver and extract that performance from these remarkable machines.
Unfortunately, Christian would not hand over the keys to any of these remarkable machines. But I still wondered how an F1 car goes from a pencil sketch to the track in less than 1 year's time, especially as the race season is in full swing.
Simulation is now a really key part of our development process for all sorts of parts of the car, but actually critically aerodynamics.
So what are some of the key engineering challenges that the team are solving with simulation?
When we think about computational fluid dynamic simulation, the biggest job that it serves probably on the chassis side is how that exterior of the car is going to be shaped. And that's not just individual components, the whole concept. It's how do we create downforce? How do we make the car heavier as it goes faster? And how do we get the balance right between downforce and straight line speed? Because different circuits require different things from the car.
Yeah.
So the journey that we go on in that engineering process, if you like, we start off with a CAD model of the exterior shape of the car. We say, okay, this is a concept that we think will work, and different aerodynamicists in our team might have slightly different variations or ideas that they might want to trial out.
Okay, I'm not an engineer, but this CFD stuff is super cool. So let me explain. Computational fluid dynamics, or CFD, helps engineers understand the forces that affect fluid flow and solve challenges related to heat transfer. Using models and advanced algorithms, CFD predicts the true-to-life physics on numerous prototype variations virtually, which helps determine the optimal design in far less time with less cost. It all starts with a CAD model, but a CAD model on an F1 car is a very complicated design. So we must take the design through a process called meshing, whereby the CAD model is divided into smaller cells, which together form a mesh. This allows for simulation of fluid flow on smaller segments or components of the car incrementally, rather than the entire thing in every iteration. That unlocks rapid design exploration, where we can quickly test and tweak a multitude of variations on the design. The goal is to find a stable and accurate solution virtually before any metal is cut. Now you can imagine this process generates a lot of data, and going back to the starting point with every design alteration is out of the question when you want to make a better, faster decision. So the data needs to be accessible and up to date, especially as multiple engineering teams are focused on different aspects of the same car.
In this era of Formula One, reliability is absolutely key. In an ever-expanding company, we need to make sure all employees are using a single source of truth for material databases and material process information. We make sure that they are used throughout the business. The designers doing the simulation work, all the way through to manufacturing that are building the parts and making the parts. Even at the racetrack, when we are doing repairs, we still need to be using the same material information and making sure the processes are as the designer has designed. So using ANSYS Grant2MI, we can overcome all these obstacles. We make sure all the data is in the right place and is accessible by the right people at the right times.
It's really getting quite difficult for me to imagine how race cars were ever built without using simulation.
Okay, so if you weren't to use simulation, what would your work look like?
Wow, this is, if you imagine going back a few years in the Formula One world, so first season was 2005, and at that point, you know, everybody's understanding of ground-based aerodynamics were just a little bit different to what they are now. And the sport was much more oriented towards physical testing. So Formula One's calendar had almost as many test events as it had race events. Part of the journey that Formula One has been going on to try and make itself a little bit more sustainable, a little bit more cost sensible, and also to embrace new technologies that are coming to the fore, like, you know, advanced CFD, is that they reduce the amount of physical testing that we get with our cars. So now, much more of that focus is on the digital world. And the lovely thing about simulation is that you can put this car in a virtual wind tunnel. You can look at how the air will move around those shapes without having to physically build anything, which is absolutely the benefit of what ANSYS brings to the table. Once we've done the sort of number crunching side, you need to post-process it and put it out into something we can really see and visualize and understand. And that's where you get those kind of iconic, really brightly colored flow diagrams where you see all the air moving around the car. Yeah. The brilliant thing is that you can do dozens of those before you have to commit to a design. So in the old days, we would have had to prototype physically, and that's expensive, it takes time, and you don't get the results for months in advance. You know, it takes a long time to actually get the results back. Now we could prototype in the virtual world, go to the virtual wind tunnel, and get data, like real valuable data that we can then correlate with what happens on track really quickly.
Yeah.
So it means that we're able to make decisions more rapidly, we're able to go through more iterative design simulations before we commit to what we think is the best one. And when we then get to the track, we have higher confidence that the car we put on track will replicate the car we saw in the virtual wind tunnel.
Yeah.
And that's what it's all about, is making sure that your simulation car and your real car are as closely aligned in terms of data as possible. And that's hopefully where ANSYS can give us that competitive edge.
Competitive edge? Yeah, I think you've got that one covered. Join us next time as we discover how breakthroughs in advanced driver assistance systems and autonomous technologies are changing where and how we move forever. I'm Miss Emma Walsh, and this is Driven by Simulation.